show of hands here, can I ask who here has held any previous role as a coroner?
As a what?
Coroner, like the guys who take apart the dead bodies.
Not to be an actual?
Actual coroner. Anybody? Okay. How about a mafia hitman? Anybody have done that previously? No, reality. Nobody?
Is the FBI around?
No. Okay, what about like a neurosurgeon? Anybody in this room is a neurosurgeon? Yeah. Just him. So, by all likelihood, he is the only person in this room who has ever physically handled the human brain. That was the only point I was trying to make. Please welcome former neurosurgeon, who happens to also lead HPCC Systems as the VP of Tech for LexisNexis Risk Solutions. Please welcome Dr. Flavio Villanustre.
Hello everyone, and thank you for having us here today. We have this structure in a slightly different way from previous years. Who has been here before, here in any of our talks? None of you. Oh, very good. Sometimes?
You mean for your product?
Previous years, yeah.
For your product?
Well, we've been here for just a few times over the last maybe 5-6 years, covering different talks, but around HPCC Systems, the platform. So this time I'm going to cover a little bit of the general things. This is who we are, what we do, and why we built this, and what it does in general. And then Arjuna will go through excellent content applying HPCC and ECL to a couple of neat problems, and he'll work out the solutions to those problems. So I hope it will be interesting to you as well. But let's get started. So some people already knew that we delivered this platform to the open source community back in 2011, but we've been developing this platform for a very long time. We really started using this platform back in 2001, 2002. We have designed the platform at a time where we had lots of data, even though it wasn't called big data back then. And we couldn't process the data with the traditional means that we had at our hands. Essentially, we were using the data processing solutions that you can imagine back in year 2000 or 1999, data integration tools and relational databases. And none of these things could scale to the volumes of data that we were handling and the complexity of the processing that we needed to do. But who we are first? So even though the platform is called HPCC Systems, we are really part of a company called LexisNexis Risk Solutions. How many of you know LexisNexis? Some of you do. So let's invert the question. How many of you believe that we sell cars? Can you raise your hand? Okay, good. Okay. Can we get something? Yes, no, we do not sell cars. We are a data management company. We do data analytics for a living. We serve professional markets. We have a number of solutions that are used by banking and financial services in general, insurance, retail, and others. We do things around fraud detection and fraud prevention, identity management, risk scoring, and other solutions. We've been doing this for a very long time. At the core of our business is we take lots of data from a number of sources, for the most part public sources or contributed databases across industries. And we build from that data the solutions that we provide to our corporate customers. We serve now customers across a very large number of countries, and more than 100 of them. Our core business was pretty much born in the US, and that's where the majority of our business is, but we continue to expand internationally as well. But what we do is quite particular because, as I said before, we get data from a large number of sources, and we integrate that data. We are talking about potentially hundreds of billions of data records that need to be integrated with maybe trillions of data points. The process to integrate that data, which is called linking, is a fairly complex process. It takes a lot of computation, and it requires to go through the data many times to be able to find those links. And unfortunately, it's something that we couldn't do with our relational database and our data management solutions back in the day. So the approach that we took at the time was to apply a divide and conquer type of methodology. Well, many of these data problems tend to be embarrassingly parallel, we thought, back in the year 2000. Just to give perspective, How many of you have heard about Hadoop? Hadoop is based on a paradigm called MapReduce that was described as a distributed data processing paradigm by two researchers from Google in 2004. We're talking about years before that. But then, nobody talked about big data. Nobody had this problem, or if they did, they weren't public about it. So we said, well, maybe we can divide and conquer this problem by, instead of buying the next biggest server that we can acquire, which was not very affordable, we can buy lots of little computers. Maybe we split the data across those mini computers, and then we figure out a way to do all of the data management across those computers. The first stumbling block that we got was the fact that our data analysts, and they weren't called data scientists back then, maybe they weren't making as much money, they are not computer scientists. They are data analysts. They understand data very well. They might understand very well probabilistic approaches to data. They might understand very well machine learning, but they don't know how to deal with problems like data partitioning, racing conditions, parallel programming, distributed programming, and other things. So we need to build something that gave them a high-level abstraction that they can program to, that makes the data and the system look like a single thing. And this is where ECL was born. So we decided to figure out a way to do this in a manner that wouldn't be too different from what they knew before. And yeah, surely they knew SQL, and we tried SQL. SQL wouldn't be as nice, even though it is called a structured query language. It is not very structured by modern terms in programming languages. So SQL, even though it uses a nice declarative approach, it is hard to manage when you grow your code base significantly. So we ended up coming up with our own language. The core developers back then were developers that came all from a fairly well-known company in the programming language arena called Borland. How many of you heard of Borland? Yeah, there you go. So a number of these programmers came from Borland, and then a company called TopSpeed that wrote and sold the Clarion 4GL language from the 90s. So these people are compiler programmers. When you ask compiler programmers to program something, they program a compiler. So they came up with this language. They programmed a compile language. Essentially, ACL, you will see that it's a declarative data flow language. Declarative programming methods, and particularly data flow programming for data problems, has become now quite prevalent with a number of approaches to this, like TensorFlow and Scale-up at some point. Back then, it wasn't as well regarded, but so I think it was a very daring move, but it was very successful. It gave us the ability to do the things with the same people that were doing the data analytics problems. They were handling them before with this single one platform, now leveraging these distributed environments. And quickly we grew out of just building the data integration problems, which is what Core tackled, and moved into the data delivery problems, which we couldn't do anyway with relational databases anymore. And that's how Roxy was born. In a slightly higher level view of our company, and I will say this because it has a little bit of applicability later on if you're looking for careers around, always opportunities. We are part of a large organization called RELX Group. LexisNexis Risk Solutions is part of the Risk and Business Analytics organization. The top company, RELX Group, is a company that is headquartered in London. It has dual, it's a public company, it has dual listing in London and Amsterdam, and some ADRs here. And it is maybe $45 or $50 billion capitalization company right now in the stock market. LexisNexis Risk Solutions represents about a quarter the RMBA sector of this company. Other divisions that you may know or might have heard about: LexisNexis Legal and Professional, which serves data solutions for attorneys. Elsevier. How many of you heard about Elsevier? Read books or publishing journals or read journals? Yeah, Elsevier is one of the largest scientific publishers. That's part of our company. And last but not least, Read Exhibitions, which you might not have heard about before. But if you attend, how many of you attended Comic-Con New York? Anyone here? Oh, some people did, but that's a company that organizes Comic-Con New York. So if you haven't heard about it, now you have. So this is what you're going to be covering with Arjuna, so I won't get into much detail here. Those are the two clusters. That's the ECL programming language, again, declarative data flow programming language. For those that think that declarative sounds scary. How many of you program SQL? Can you raise your hands? Very good. SQL is a declarative programming language, so there you go. It's not that scary. And last but not least, and I don't know how many of you might be looking for internships here, but if you have friends that look for internships or friends that would like to find opportunities across the industry, we have a number of opportunities for entry positions and for internships as well as senior positions across the entire organization. We are part of technology in the organization, so I can tell you about internship opportunities in technology and jobs in technology. But I can also introduce you to other areas if you are interested in other things. Keep in mind that for a company that makes data as its core business, we have careers across data, and many of these careers can seem a little bit different from what you would find in a more run-of-the-mill company. One of the careers is becoming a data linker. So data linking is a career in our case. And data integration and data loading and data processing is another career. Data querying is yet another career in data. As you can see, many of these things that tend to be all covered by one person in most companies are entire careers in a company that does data for a living. That's slightly different from what you can see out there. Just to pass this to Arjuna. Arjuna has been with the HPCC Systems area of the company and project and community efforts for a very long time, for longer than it has been open source. And it's one of our people with the most expertise around the platform and integration of the platform with a number of other systems. He's done a nice job integrating, for example, with Spark. Someone mentioned Spark before, and Hadoop and other open source platforms. And we try to integrate as much as we can with open source. We don't want to reinvent the wheel if we don't need to. And he has developed quite a bit of content around use cases and application around the platform. So we will have Arjuna now cover all of that part. But before we get there, I'm sure Jessica, who is around here somewhere, will not be happy if I don't remind you that please, you should go and do the trees thing and get a trees planted for you. That's quite important, otherwise you will hit me later, so make sure that you do that. Thank you. Arjuna, all you.
Internship program only for students, undergrads, or only for school kids also?
Not necessarily. We cover all the way. Anyone, really. We have this. Of course we do, yes. We had 2 high school students so far. The first one was last year, 2017. It was a fairly difficult, so we were used to, for the longest time, to do graduate students for these programs. Eventually we go to undergrads, and they require a little bit more hand-holding, but it's not too bad. When we went to high school, they do require a little bit of hand-holding. It was a little bit of a disruption in the way we thought about it, but we did it, and it went very well. So well that we decided to continue to open the internships for high school students. So yes, absolutely. And for high school students, most likely we would like them to be local to one of our offices because we can. We could. We have offices in New York as well. In the only building that is standing on top of Park Avenue. That's our building there. But otherwise, in any of the other cities where we have presence, it's probably better because we can do more hand-holding there. When we do internships, we require that our mentors, and most of them tend to be LexisNexis mentors, but there are sometimes community mentors outside of LexisNexis. We require that they dedicate at least 10 hours a week to students, and more in the case of high school students that may require a little bit more hand-holding, as I mentioned before. But yeah, absolutely. High school students, they're welcome. Yeah. Okay.
Thank you, Flavio. Before I get started, I want to show you 2 URLs that were not mentioned in the previous one, mainly because it's new. Note it down. If you have a laptop or phone, go to it, take a look at it, because it covers a lot of interesting content, including some real use cases, right? So that's one of the URLs. Then the more interesting URL, probably what you want to check out is an actual HPCC cluster itself, right? If you don't want to learn by installing everything from scratch and getting to know HPCC. You want to get there a little quicker, you can go and play around with the playground, which is online right now. Okay? How many of you have heard of what a data lake is? Or how many of you use a data lake at work? Can I ask you in what context, what technologies is that?
The system where we run it on is running on a Google Cloud platform, and all of our data sits in various what are called dispositions underneath various storage buckets depending on the security.
Yeah, perfect. Yeah, that's a great example of a use case for data lake. Similarly, I'm pretty sure some of you use AWS in some ways or form. You can regard that as the data lake solution, actually, especially if you use S3 as the integration hub for storing data and then exchanging data with all the other tools like Redshift, Kinesis, all the ecosystem of AWS services around that. It is, in theory, a data lake by itself. In fact, I think AWS, if you look at the latest literature, they're promoting it as a data lake solution. Interestingly enough, I presented at 2 universities recently, and when I approached the students, and this is a data analytics class or data mining class, and when I approached the students and asked them, what is a data lake? None of them knew what a data lake was. Right? And for me, that was kind of surprising, because in the data mining field, if you're doing anything with regard to analytics, something like a data lake becomes core, because that is the concept of bringing all your data sources and data together into kind of a logical single block where data scientists can analyze. Does that make sense? So it is a really important concept. By the way, how many of you have come to actually code easier today? Not many laptops. I guess we didn't send the message correctly, right? But anyway, no worries. We'll take you through some examples. That was my main intention today. And hopefully you'll get a basic idea of what a data lake is, and then some confidence on what ECL is and how it fits the paradigm of a data lake, right? And how it helps in data lake programming. First of all, what is the need for a data lake? It all starts with volume. From perspective, Flavio talked about how LexisNexis gathers data from literally thousands of sources and brings it all together to perform analytics. For example, we gather data from every public records courthouse in the United States. That means every county has a courthouse. There's somebody going to the county on a daily basis, gathering the data and pushing that information back to LexisNexis for processing. So tomorrow, somebody goes out there and does a check on a person for employment, and he has a criminal record. They want to know about it, right? So to perform this level of sophisticated analytics, we need a platform that can understand data very quickly and be able to analyze it rapidly. If it is not agile enough, then you will not be able to process it very quickly. So volume is one of the factors that why a data lake is needed. Second, velocity. So, how many of you, when you go to a fast food or any restaurant, wonder really, is this food that I'm eating organic, not organic? What does it contain? Have you come up with questions like that? Yes, obviously, if you're eating something that is, I guess I probably do not need this. Can you hear me clearly?
No, you do.
Okay. Okay. So the idea behind one of our customers is to actually solve this problem. Partly solve this problem, but also solve the problem of farming from the perspective, how do you make their process very efficient, right? For example, they have this concept of a Fitbit for cows, just like Fitbit for humans. So it tracks the ecosystem of the life of a cow from start to beginning, right? How is it performing? Is it getting sick? Is it going through the process of eating well? All that is recorded. Not only is it recorded, it's also fed into systems almost in real-time fashion back to a central hub, which is processed. In this case, HPCC is used as a central hub. So if there is something that needs to be done, we can instantaneously act on it, right? If you look at a single farm, it might be fairly easy to process this data. But if you look at a farm, a lot of farms across the United States and Europe, all collecting data and processing at the same time, it becomes a fairly large problem. It's not a trivial problem, right? Same thing with farm management systems itself. How are crops grown? What is the best season to do the seedings? What is the fertilizer used? Is it organic, non-organic? When is the best time to harvest it? How is climate affecting the crops? So all this information is fed from the farm management systems back into an HPCC system, which again performs this analytics and feeds quite a lot of the analytics back to the farmers itself to better manage their farms, right? And now what they're doing is, on top of that, this particular information is also being fed to regulators. So when the regulators see this information, they are able to then say, is this farmer performing the task that he's supposed to be doing, right? Is he using the right content? And eventually that information will loop back to end consumers, like you and me. Make sense? But this is something that is really catching on very quickly as a use case. And you'll see, maybe I would say 2 to 3 years, you'll see a lot more information flowing to consumers in this field. So velocity is extremely important in a data lake application, right? So the amount of information that's coming in and the rapid action that you need to perform if something goes wrong is a data lake use case too. Then variety. Right? What do you mean by variety? So if we were to gather data from a single source, even though it can be large data, maybe terabytes or petabytes of data, there will be a lot of inaccuracies in this data. Okay? Now, if you instead gather data from many sources and then bring it together, you'll see those inaccuracies or holes in the data slowly but surely disappear over time, right? And that is essentially the technique that LexisNexis uses behind the scenes. They don't depend on one single data source. They depend on thousands of sources. Because depending on one single data source, even though they say they're the most accurate, is not going to be accurate enough for a LexisNexis use case. In our case, we need to be 99.99% accurate. Otherwise, somebody doesn't get a job, or somebody gets fired, right? Before I go into the slide, can somebody point out what are the differences between a data lake and a data warehouse? Structure. Okay. When you say structure, when you...
Our data warehouse in the SQL context has fact tables and dimension tables, and you are structuring a result through the dimensions you use to come up with the information.
Okay.
But a data lake sounds like it's just unstructured data pointed to create like machine learning.
I think you're almost there. I would argue that in many cases, even in data lake, you can have structured data. Go ahead.
A data warehouse, usually the data is collected for specific use, so many times what is considered trivial or unimportant data isn't included
In a data warehouse, which is true. Which is true. So I think, to be a little more specific, I think the term that we use is data warehouses are schema reliant, right? In the sense when you talk about structure, without the structure being present, you cannot even push data in, right? Whereas in the data lake, it is not schema reliant from the perspective, it does not expect the schema to actually push the data. You can apply the schema on read when you actually do processing of the data. So what does that give you? That gives you a lot of flexibility from the perspective of observing data. If there is a field that is missing, or if there is something wrong with the data that is coming in, a data warehouse, you bring in the data, it will blow up, right? And then suddenly everybody is scrambling to actually go fix the data. In a data lake, you can absorb the data, accumulate it, and then also you can catch those errors when you're processing, and then fix those errors or apply techniques to actually enhance this data.
We're talking like staging tables to the stage process. We accept everything in staging table and process. So then we apply all the logic.
Which is almost similar to what we do in a data lake, but you'll have to do that extra bit of processing to create those staging tables and do the processing. You know what I'm saying? It's not a natural fit into a data warehouse. It's like something that you thought of, okay, to work around the problem of doing. Whereas in a data lake, the out of the box, that's the key concept. Okay? Go ahead, you had a question.
Well, it would seem to me in a data lake, you'd also have the issue of dimensions because trying to classify such unstructured data, you'd have to have many, many, many kinds of dimensions to make it work because you won't have any centroid definition unless you have some sort of classification scheme that you could do by having many, many sets of equations.
That's true. And actually, let's hold the thought for until I show you an example, and you'll see how you overcome that potential drawback in a data lake. Right? Because it's a natural progress in a data lake where we have to do this anyways. So
another thing that looks to me is maybe the data warehouses, they don't process generally the graphical data.
Pardon me, say that again?
Graphical data.
Graphical data.
Like blobs, we don't process the blob. We cannot read the blob.
Sure.
But the data lake maybe
that's true.
Enables
that's true. So specifically, again, one of the key concepts is just like how you guys use Google Cloud in your case and AWS. When you go into using a system like this, you think there is infinite amount of storage. You're not really worried about bringing in data into the database, right? Whereas in a data warehouse, first thing a data DBA will ask you is how much data, right? And by the time you convince him this is not much of data, it will take you a few months, right? Whereas in a data lake, there is no issues in bringing how much of a data you want. So in concept, you can have infinite amount of data in a data lake. That's one of the key concepts. If it doesn't satisfy that, then it's probably not a data lake. Okay? And then schema on read, that's something that we just spoke about. That is really important because that gives you the flexibility to process the data after it comes into your system. Okay? Obviously, low cost of storage. You can't spend millions of dollars on a mainframe to create your data lake, right? So we want to make sure your compute and storage is cheap. So commodity hardware, commodity software. One important thing about a data lake is something called metadata tracking. In the sense, if you do not know where your data points are in a data lake, then what does it become? What is it called? There's actually a standard term for that.
Garbage.
Data swamp. It's called a data swamp, right? So that is the important thing. What distinguishes a data lake from a data warehouse to a data swamp is these attributes. Now, Flavio mentioned this. The basic premise of any big data compute platform is the divide and conquer, right? What a lot of the people, when they talk about Spark, Hadoop, or HPCC systems, forget the actual architecture behind the scenes is really almost exactly the same. In the sense, data is divided into chunks and then processed in parallel. Do you know why they do that? Why is this an effective methodology? Even for any data processing job today? Because we have realized that 80% of any data processing that you do, like transformation of data or performing some level of analytics, is inherently parallel. Okay? So they're parallel in nature. So that means you can divide the data. Parallel. Sorry about my accent, but yeah. So they're parallel in nature, in the sense that you can literally divide your data. For example, divide your data across multiple laptops and execute a command in parallel to work on those laptops. Does that make sense? And we have seen this in LexisNexis or our experience of 20 years in data processing. That's why HPCC is so effective in the way it is used in LexisNexis. Just because over time we have realized most data processing jobs are highly parallel. Now, there's a limitation. What is the 20%? The 20% is when you need to start building potentially a machine learning model, where during the process of building that model, there's a dependency of, okay, I run my first iteration, I run my second iteration, is it converging? So there's a dependency there, right, between different iterations. So that is when it will start diverging into something like other techniques that you probably want to use other than parallel, highly parallel techniques like this. But even there, newer algorithms in machine learning, they're trying to implement it in a very parallel fashion there as well. Right? The traditional algorithms are being converted into highly efficient parallel forms even in Spark. So if you go and look at machine learning algorithms in Spark, they don't implement the whole suite of machine learning algorithms in Spark, right? They have a subset of it. The reason is they have found a way to actually parallelize those subset functions where it is very highly efficient.
So I have a question. Isn't the main reason we're doing parallel for speed because we want almost real-time response? Isn't that the main reason for making things parallel?
Yes. So the key is, as a data lake, it has to be by default high performance. Okay? Now, what I was showing is how do we achieve this high performance in a sense in any data lake, right? Whether you're talking about Google Cloud or AWS, in AWS, if you go and use some of the services behind the scenes that are actually using Spark, even though they're calling it Athena, Kinesis, but behind the scenes, the underlying technology that is used is really Spark. Okay. Now, going back to HPCC and why HPCC really is a fantastic technology as a data lake technology is because it satisfies all the criteria that I showed you in the previous slide, right? So literally, you have unlimited storage. Data can be stored on landing zones, which can be S3 in theory, or just landing zones, file systems, deep storage. Data can be stored on our cluster. Are you sure you don't work for LexisNexis? Because you've been able to answer all the LexisNexis questions. So anyway, so data can be stored on the batch flower cluster. Data can be stored on the Roxy cluster. Now, these clusters by itself can be interconnected together to form n number of clusters. And the data across all these clusters can be tracked through a common middleware services there. Okay? So that means, in theory, if you look at it, it satisfies all these criteria that we spoke about in a day life. And it's a single system, single architecture across the board. Right? We talked, as I said in the beginning, I showed you those two URLs. The reason why I showed you those two URLs is I obviously cannot cover all the details in this talk, but that URL is there. You can go and read through that and you'll see all the details explained there. Why you're talking about it.
If the VS Code is Visual Studio Code?
Yes.
The open source Visual Studio Code?
Yes. So, that is what I was about to jump into. Now, coming to coding a data job in HPCC and ECL. In HPCC, we use a programming language called ECL. Flavio talked about exactly why we had to invent ECL, mainly because we wanted to make it easy for a domain expert to work with data. Right? So I might be a very good developer in theory in Java or Scala or Spark, but if you go and tell me to work in, let's say, the agriculture domain, I do not have knowledge of the agriculture domain to actually make any sense of the data that you're providing me. So we wanted to give the power of data analytics to the domain expert. And we wanted to create a simple enough programming language to do that, where he does not have to worry about parallelization techniques, too much on the if then else, control flow, all that. Take it all out and you just really concentrate only on the data part. Right? And hence, we invented ECL. Right? Now, the VS Code, as you mentioned, is a newer IDE that is supported. So we have an ECL plugin with VS Code. I'm going to demonstrate that in a few minutes. But it is full-fledged. You can do all your end-to-end ECL programming within VS Code itself. Okay? Now, so let's talk a little bit about the exact execution flow of an ECL program, which is important because once you start playing around with the playground and ECL, you'll understand it better if you understand this data work. So a programmer puts the ECL in VS Code, he submits a job to a middleware services layer in HPCC, which compiles it into what is called the data flow graph. Everybody knows about explain plans in the database, in Oracle and MS SQL, right? So, okay, let me ask you this question. How many of you have actually seen an explain plan? So when you see an explain plan, let's say you execute a select, whatever, table name, this, and suddenly when you see an explain plan, have you wondered, why is it using this index? Why not this? Why not this? So you will see that the database engine, based on the data that it has about your query, has optimized it to a large extent to make it very efficient. This is exactly what happens in ECL as well, right? The data flow graph is really your explain plan. But with the added complexity, it's not just working on one single node. It creates the explain plan to be efficient on a distributed set of nodes in a cluster, right? Hundreds or thousands of nodes working in parallel. So then after that is deployed, and by the way, that whole explain plan and also subroutines that execute each activity in that explain plan is compiled to a C++ DLL and pushed to the cluster, and that gets executed on the cluster. That is the entire data. And then if you go to the playground and if you look at some of the work units, that's why I showed you that up front, because if you want to play around, just go look at any of the work units that they as executed, and there's an output tab. When you go and look at the output tab, there's a link to graphs. And for each of those work units, you see what the explain plan is. Okay? In fact, that is going to be one of the key debugging tools for you when you start working in the ECL. Right? Now, remember I said ECL is simple. Essentially, boils down to, almost everything boils down to this 5 steps. Okay? You have a data set, which is equivalent to your RDD in your Spark, or whoever's using Spark, right? Data set is similar to that. And you have input file, like the training, sample, stacks, in yellow, it's referring to a logical file on disk, right? And then you have a schema that you define when you execute the code. This is what I mean by schema on wait. Now, this schema is not predefined somewhere. It's defined in your code to explain to the compiler that this is how you want to map this data that is coming in and start manipulating it. Right? I'll show you another example where I switch the schema to look entirely different, because I know more details of this input file, so I can literally say it has these fields. Okay? And then the third step is your activity. Those familiar with Spark, project is equivalent to your map function in Spark. In the sense, you're simply saying, go through every record in this data set and apply a transformation on it. Okay? And what is that transformation? Essentially that. You're basically converting the whole record to uppercase. That's one single line.
What is the purpose of this code? Is this a model? Is this a representation of a data set? Is this a machine rule? What is it?
So this is essentially doing ETL stuff, right? So it's literally reading data. So when you see some of the things that we do in the next few slides, you'll understand there's some standard things that you have to do as far as data processing is concerned before you go into something like machine learning. But this is literally your almost the first step that you do. But in everything that you do in ECL, this is the same pattern. Okay?
But how do you're saying that this is defining taxi data. Now, do you already know what the data looks like, or you're hoping that it looks like this once you define it?
We know what the data input data, raw data is from our platform. In fact, it has a lot more information than a single line in each of those records. But what we meant by showing this example is, you can interpret that data as you want it when you read the data during the ECL program, right?
So why, it seems like you're adding a step you don't need.
That's true. And the reason why I showed this example is to show you there's an alternate and better way to actually do it in the data step. That's what I'm going to show you now.
What stands for ECL?
Enterprise Control Language.
It looks like ETL, right? Extract, transform, and load. ETL is same thing, extract, transform, and load. Right? And we are saying here extraction through the schema. How it should be extracted.
So,
transformation is your activity and transform. And I don't know about the action, but once it's extracted and transformed, data is for loading into something else.
yes,
That's what ETL stands for. But here ECL, what is the difference between the ECL?
So ECL, even though we do use the term ETL, HPCC by itself does not extract data from third-party systems. You know what I'm saying? When you're talking about an ETL tool, The concept of E is about extracting and integrating with your third-party databases. I'm going to fetch my information from Siebel, I'm going to drop it into this database, do something with it. HPCC by itself does not give you the capability to go and fetch from Siebel, right? It does not have connectors to do it. It's not a typical ETL tool from that perspective. The idea is you push data into HPCC. Don't worry about in whatever format it is on the other side, right? You push all your data into HPCC. Like, for example, in many cases what we have proved is, instead of using your ETL tool, you simply export your data from your database and push it to HPCC, which is simpler and much more efficient in many cases. And that is what this does. Executing all the code together, whatever steps I should and execute it on the playground cluster, that should execute. Similar to the project operation, we have other operations to do specific things, just like how we have like flat map, Spark, etc. etc. So roll up is to bring up information together, just like what flat map does in Spark. It's equivalent to grouping information and then aggregating, right? Iterate, you can work across 2 records at a time. If you want to manage the 2 records at a time and pass the data set, that's what iterate does. Join, obviously, joining 2 data sets together. Normalize is about working with concepts of child information. So in HPCC and ECL, you can have a tree-like structure. It does not necessarily have to be flat. Think about working with JSON or XML. Then the concept of normalize comes, normalize and denormalize comes into picture, in the sense that you want to regard this as flat or you want to regard this as children. Right? So those 2 functions are there for that. Table is more to do with the SQL-like aggregation and manipulation. Okay, now let's look at a real-world use case, right? So we're looking at trip data from, this is again open source data set that's available. You can just Google it and you'll see several sources of information to go and access this data. And we are referring to that. And the whole source code is available in the link that I showed you earlier as well, right? So 1.3 billion records of trip data within New York in 2015, and I think it's collected till the middle of 2016, right? So every trip for a Uber drive or a taxi drive is a record. And some of the interesting fields, now going back to what you said, we know more information about the data. We do. There's all this definition of vendor ID, pickup and drop off date, passenger count, land loan, payment type, what was the fare amount, all this information comes in from the input data set, right? What I regarded in the previous example was a single line. We actually know much more about that, and in fact we can simplify that with a much more simpler example. Now, for anything that we do, any data analytics job that we perform these key steps. I actually left out one step in between, but we'll talk through that. But the obvious steps are, okay, you import the data into HPCC or your data lake, validate the import by doing some analysis of the data to make sure it's valid data, right? If it is garbage and you don't even want to clean it, right? Then you clean it, you enrich it, you do some analytics on that, and potentially do your machine learning. For your machine learning, you want to create a training data set, build a model on that, and export it, right? So this example that we have takes you through all those steps. So if you want to go through how you want to accomplish this in HPCC and ECL, this is the example that you want to take a look at. Prerequisites for this, you need VS Code, obviously with the ECL code plugin installed on it. And you want to know a little bit about how ECL watch works, right? That is the reference to the playground that I showed you earlier. How much time do we have? Okay. Now, going into the VS Code itself. So by the way, all this code is checked into the GitHub site there, so you can literally, when you go home tomorrow, day after, whatever you want, feel like playing around with it, just check it out and execute it. Yeah, you know, the code will work. Right? So again, one of the first things that you want to do with the data is,
can you zoom in? Zoom in?
No, zoom in. Let's see. Mirror? What is this?
Control and
Mirror? Okay. So essentially the first step that you want to do is bring the data from the landing zone, what we call as the raw data area. Right? It's a storage area where we keep the input data that comes into the cluster in raw form. And then from there we import it into the HPCC cluster. Right? So what I have specifically, this relates to the data that is there on that playground that we have. Right? So we have the file that is sitting in this thing as this file physically on the cluster. So if you go and look, now I'm quickly going to brush through some ECL concepts here. Obviously there's a lot to learn. There's a place where you can look at the landing zones. And then we have some sample data sets already there. And the data set I'm really interested in is this. So what I'm going to do is I'm going to fire a job which actually does the import of this data set into HPCC. There's several ways in which you can actually import the data. You can import the data straight from here by selecting the file, and in this case it's a delimited file. I can specify the import criteria and import the file into the HPCC cluster. Right? But I do not want to do that. I want to do it through code, because once I do it through code, I can actually then create an automated job around that so that it can run daily. Right? So the idea is to show you how to do that. Very simple. And the whole concept of HPCC right from the get-go has been based on implementing everything as microservices. So literally anything and everything that you see in ECL Watch can be invoked through a microservices invocation by yourself, and then you can get that information. Right? Whether it's metadata on the file or all the work units that are executing, what is the status of the work unit, you do a web services call, sub services call, you get that information. So similarly, using a standard library function to do the import, data file import, you execute this, hopefully. Let's do a live demo. Completed, right? So it was successful, worked. Let's go look at the playground logical files. Be filter about something I'm looking for. Thanks. Essentially, this was the data file I just imported, right? And look at the date on it, it says today. So I'm not making this up, right? So if you look at the criteria and the specification that I have, the name that I provided is this, which is in fact defined in files info. And the file output file name is this. So essentially, it's created. Now, the interesting part of what I want to show you about this file is literally the raw information is it doesn't understand what the format is, it's all strings, so there's no field definition to it, so it comes out as raw information, right? Now, when you go and look at what is called as file forms, you'll see, remember, we talked about how the data is divided into parts. HPCC, when you imported the file, is already done that for you. Why has it divided into 4 parts? Because when we configure the cluster, we configure it with 4 executors or slaves. So there are 4 parallel executing processes working in the node, right? So automatically, when we import a file, it chunks it into these 4 parts. Any file is divided into 4 parts, and when you operate on it, it's 4 parallel processes that can work on the different parts. Does that make sense? Now, going back to why did I do all that single line to one line? Well, I wanted to show you an easy way to do it, a little more straightforward, I wouldn't say complex way, but straightforward way to actually map the data into HPCC. Now, since I know that this is the record structure of the input file, I can actually define that in ECL, saying, okay, my input file is really a CSV file, and it has all these fields in it, right? So, literally, I make up the field names, and initially make it string, right? We'll optimize it a little later, but initially it can be regarded as string. But the idea is to read that in as a well-defined data set, and then display it. That is essentially the first step that we want. And once we read this definition in, the next thing that we really want to do is do some cleaning activity on this data set, right? So one of the things that we do want to do before we get into anything else is actually optimize this layout, right? When I say optimize this, string, defining everything as string does not give the ECL optimizer good enough information to make it very efficient to handle this data set in memory. So it needs a much more tighter definition of how big a vendor's ID field is, or a passenger count field, right? It cannot be just a string information. So if you can make it as narrow as possible, it will make it much more efficient to execute when it executes a job. Hopefully that makes sense, right? So now, so to do that, next, I define a cleaner layer, right, which is much more specific. So I have date fields well defined. I have a vendor ID, which I have realized that is really, unsigned 1 would be more than sufficient to store that. Same thing with passenger count. So all of these fields that were free-form in the beginning as strings, now I have a much more detailed layout of the file, right? How did I find this layout? That's the one step I did not explain in the whole process, which is actually a fairly complex step to walk through in this particular workshop, but that is called as a data profiles. So we have a utility called data profiling. So you can point any incoming raw file to this utility, and it will give you all the stats of your data file. In the sense, what is the layout of this file? What is the optimal field structures of this file? What does this field contain from a alphanumeric content perspective? So essentially, once you look at the data profile report, you can then determine this is what my so go ahead.
Does this do any coercion? So, for example, if I have a CSV that's 8.2, and all of a sudden I got like 100 units that are 8.3, does it crap the bed, or does it go, hey, this is actually 8.2, I'm going to do the rounding here, I'm going to...
You can do the rounding, yeah. You force it to the rounding, but before you, that's what I said, before you do that, you definitely want to run the data profiling report, because that is a very essential step from the perspective you do not want to lose a data point by accidentally compressing it. Right? So as much as possible, what we try to do is we try to keep the original data point as well as the one that is optimized, if needed. Right?
And if you have cell drops, like my rate code ID is not there, does it put it in default, or does it just, how does it handle missing data?
So let's go to, good question. So let's go to the code. So this, until now what I've done is I've simply defined the layout, right? So this is like the schema that I want to read in and optimize, okay? So remember, when I read the raw file, it's all strings, right? Now I want to be able to convert this raw data into something that's more well-formed like this. Does it make sense? Step A is to just read the raw data and then convert it to a cleaner version of the data, okay? So essentially that is what my clean job is. And let's go take a look at the clean job.
I have a question. I'm just looking at the GitHub code.
Yeah.
It shows a class called data patterns and then the method of dot profile.
Right.
Is that all you do when you say profile? Is the calling the class and running it?
Exactly. Yeah.
Or are you actually, then how do you visualize the data?
So you go to ECL watch, and the ECL, in the ECL, when you run that, now when it shows you the output, it kind of shows you in a channel record set, right? So basically, it will show you the layout of fields and what this field contains, and it is more of a tree-like hierarchy of information.
But is it an iterative process for the profiling, or is all you do is run that method and then?
It's just one job across the file. Give it a try, and you'll be amazed how the thing works. So here, essentially, what I'm doing is simply converting the input data formats to cleaner versions of the data.
My problem is that the only thing that I have a problem with is passenger count, and that's the only thing that would be input manually.
Passenger count.
Well, the cab driver has to put in how many people.
Right.
Everything else can be picked up from the meter. And I'm wondering why there would be less than 0 passenger count.
That's because when we profile the data, that's exactly what we found. We found that there were -1s.
There were zombies.
Yeah. There were zeros, and there were like others which were like 20 passengers in the car. So,
well, the people before you, the meetup we had last week, they did analytics on taxi rides.
Right.
And they said, they showed us.
yeah, and then when you run that profile report that on this New York taxi data, you'll see that. I can spend literally half a day on just that, that profile report. That's why we did not tackle it during this session. It's a pretty detailed report on the discrepancies that is there in the New York City taxi data. By the way, an assumption that anybody would go with New York City taxi data is by assuming that, everything is clean, right? That you start with that, let me start building my machine learning algorithms. That's the assumption. But your whole assumption will be wrong because your data will not be as accurate as what you thought it would be. And we have seen this over and over again in several use cases. In fact, last time I did a workshop, it was around simulated telematics data. Simulated telematics data in Cologne, Germany, right? So this was not data that was coming in from the actual field. It was done by a software. It was simulated by a software. And that had many more errors than a New York City taxi data set had, right? Initially, you would think it's a simulated data set, it should have 0 errors, right? But it had many more errors than what we see here. So making assumptions, that's the critical mistake, number 1 mistake everybody makes. Making assumptions on the data and jumping to the conclusion at the end. They go to the obvious solution. They don't look at the non-obvious issues that are there. Yeah, go ahead, please.
If statement, cleaning up the passenger count. Am I reading this correct, that it's the conditional? If the condition, put it 1, otherwise just leave it as is?
Yeah, that's what you've done there. Okay. Exactly.
Okay.
And if you, to get you started very quickly, obviously the key thing is understanding of these concepts. Remember the 6 steps I talked about in ECL, that is critical. And then good knowledge of using the standard library. Right? So it's one single PDF, download that. You'll see utilities for passing date, strings, manipulating regular expressions, all that built into the standard library. So if you have these two, you can do a lot of work in HPCC and ECL straight out of that.
That's great. No, sorry.
Any questions? So this, again, run this. Let me show you one run and then you just jump into your other solution very quickly, right? Otherwise it's going to take you over. By the way, before coming to this workshop, I made sure I ran it in the hotel. Make sure, I have a copy of it actually working, just in case the demo fails. 5 minutes. You know how it is when you're actually doing a live training, most of the time fails. Okay, so in any work unit that you run is available. The information of that work unit that I just run, what the output it's produced, what the metrics on that work unit is available in the ECL watch interface under work units, right? So you click on that, give rough information over here about the actual work unit itself. But the most important one that you really are interested in actually is the output or the outputs, right? And in that, the context. Remember, initially when we saw the raw data, it was just one line, right? It's just a line as the heading. Now we have parsed it into the different parameters which are optimized. Now, from this stage onwards, when we use this definition of the data, HPCC and ECL can optimize it to a large extent based on how much memory is available in your system, right? So one of the key issues with any data processing job is when you overflow memory. Right? When you're doing it in job processing and suddenly you run out of memory, it starts spilling into this. Right? When you define it tightly like this in HPCC and ECL, the optimizer then understand how much memory you need and at what point it has to be spilled to disk. So that is automatically taken care of by the ECL optimizer for you, right? So again, going back to a domain expert having to work on data, he does not really have to worry about disk spills, when he has to optimize it, nothing, right? He just writes the ECL code, what he wants to do with regard to solutioning it, execute, look at that. Okay, now I'm just really going to go fast on the other aspects of it. So, similarly, I have steps to enrich the data a little bit from the perspective. You see the data itself, when you go look at the file layout. It does contain important information, but I want much more finer granular information because I want what time of hour is it. Right? When the pickup happened or when the drop-off happened. Because then later on I can aggregate the information to that hour in the day to saying at this hour there were so many trips. So based on that, potentially I can build machine learning algorithms for predicting future traffic right? So to be able to do that, I have defined a newer structure called enriched structure, right? So, and in that structure we have defined more granular fields like this. Pick up time of hour, drop off time of hour, pick up year, drop off year, so you can then drive aggregations on those fields individually. Okay? And once we have defined that structure, and this is what we want to do, then you have to write the code to actually do it. And that is what the enrich job essentially does. Right? So it calculates all those fields individually for you, so that then it's much more finer grained detail, and then you can perform more analytics in the future. So to go quickly through other steps. Now, the analysis job really talks about aggregating information. Specifically, for example, in this particular case, I'm looking at, for a pickup day of the week, what is the volume? Right? For example, on Wednesdays, what is the value? So if you want to express this in SQL, select pickup day of week, count from taxi files, taxi MSDS group by pickup day of week. So that is the equivalent of the table function that you see in ECL. It's the same, essentially. So I have some more examples here, and if you guys want to play around, I've asked a few more questions for you to answer to start with. But what is going to happen is, if you really get into it, you'll start doing all kinds of fun stuff like this, into understanding the data and building more attributes, which is going to be very helpful for building prediction models in the future. So in my case, I've created a simple training set for running a generalized linear regression model on it. Very straightforward algorithm that is executed in HPCC. So what I've done is, for a year, month, day of month, and day of week, you can combine that as a group. What is the volume? What is the count? Right? And based on that, what we're trying to do is, if given a future day, what would be the volume? Right? Given a month, day of the month, and weekday, what would be the future volume? For example, you're predicting taxi traffic next week. Very simple example. With this specific example, yes, you'll be able to build a model and do some prediction. Not going to be very accurate, right? Because you still don't have enough data points to be able to build an efficient model. What I would do is, I would also consider weather, right? Then different areas, for example, in the New York City, potentially you are aware of as far as traffic restriction, construction, all this comes into play, right? Bring in a little more data sets, make it more enriched, and then build a model on that. That would be really, really interesting. Okay. And how to build a model. So, just a little bit of information on the ML support in HPCC. We support a bunch of routines, right? The whole general linear regression models. We support a few algorithms in that, or a few distribution models, right? We also support random forests. We also support decision trees. Support vector machines. Why don't we support like all the ones that are supported in R? Because the key challenge in any distributed data environment is to make these algorithms highly parallel and efficient. We have been able to make these algorithms highly parallel and efficient. So when you use these, you're guaranteed to get a good result, first of all, and it's going to be very efficient from a speed perspective of execution. That might make sense? So that's pretty much what I wanted to cover in this conversation. So
you don't support deep learning in neural nets. It's only random forest, SVM, decision trees. What else do you support?
For deep learning, we do support the number of, we have a number of components already defined, created, deep learning, that includes sparse autoencoders, that includes efficient distributed optimization algorithms, like LBFGS, for example. And a number of basic modules that you might need to combine to build your deep learning model. This is your network structure. We haven't added all the glue yet, even though there is a researcher right now and 2 students that are working on extending this to add the extra glue to build a complete deep learning model. There should be something out ready within this year. It's currently usable, so you can use it. It just doesn't have all the nicely glue integrated. All of the other things that Arjuna was covering, they do have a complete glue, so you can run it as Arjuna showed with a single attribute definition and then execute that model against new data.
Yeah, the one thing, if you're trying to execute this on the general playground, it'll come back with an error saying that you cannot execute embedded code on the cluster. Since it's a public cluster, we have restricted it to execute what is called as embedded code within ECL. You can embed C++ code. The ML core libraries uses this embedded functionality to do some of the math functions. So that's why you see that but we're going to make it a little more lenient in the future, and you will be able to execute it on the playground itself. But there's no restrictions for you to actually set up your own cluster and execute it, right? Literally, you can set up a HPCC cluster in 10 minutes.
You can run a virtual machine in the lab.
Sure. Oh, sorry.
One last question. Is it possible to take this data, like say you want to do a specific neighborhood, like say Williamsburg, that's going to have the L-shaped one, and be able to take that data and be able to create more patterns of traffic?
Yes, absolutely. And in fact, the one that you saw with regard to the data patterns, that has that part of the code itself. The reason why I did not show it here is that's pretty advanced. It's not linearly explained like what we have explained in the tutorial fashion, but that is a real example of working on the data itself.
Yeah, I saw the joint with the weather.
Right, and it does the boroughs divided, right? The areas, different areas divided. Aggregations are performed based on this area. It also has the weather data integrated as well inside that. So I really did not want to start there and confuse the heck out of everybody. I wanted to start in a much more linear manner. But now, I think once you get these concepts well understood, it'll be much easier to go and execute those concepts. Any other questions?
Can you put the URLs back over?
So this is essentially the HPCC Systems repo, right? A lot of sub-repos or projects are exposed here. What you are most interested to start off with is this one, right? Which talks about whatever I just spoke about, end to end, and even much more detail is in this repository, okay? The code examples is also there, right? It's the same thing that I just executed is here, end to end, and it's in fact explained as a wiki as well. So that is one of them. The other one is the actual cluster itself. So we have a cluster. What we're going to do is make this is kind of an open cluster for you to go in and play around, simple queries, etc. But what we're going to do is make it a more multi-tenant type of application where we do your login. When you go in and log in, you'll have only your area to work with, right? So your landing zone, your work units, so you want to see a global view of everything that is happening on the cluster.
What data sets do you have built into the cluster right now to explore and play with?
Not much right now.
Is that taxi data set that you were talking about in this?
There's a few more. Yeah, there's a few more. You can go take a look at the landing zone. There's a few more data sets here. But one of the things is this cluster is our original intent was not to make it a global cluster for all experimentation. We just wanted to make it as a playground to execute small ECL code snippet, right? But now, with the interest that is growing, we want to make it a much more robust cluster with potentially open source data sets already available and code also available. Right? So people can get started very quickly
That is all the time we have for questions today. However, our speakers will be here for one-on-one questions right now after our raffle. But before we do the raffle, I want to give a great big round of applause to Arjuna Chala and Dr. Flavio and Arjuna. Who wants to win a Kindle Fire? That's not even all the hands. Come on. Someone with their hand up is going to win. All right, can I ask you to just reach in and mix it all up? It's really not mixed, so try to mix it better than that. You're all going to stack. Oh, he's taking this seriously. It's like a poker player. Look at that. All right, just dump him. That's good. You're like a casino worker before? Alright. Can I ask you to reach in and look the other direction and pull one out? If they were written in Braille, you might be able to cheat, but otherwise you can't see. Read it out?
Not sure if I can pronounce it. Und hi, Tunayan.
Oh! Thank you all for coming. Our speakers here for one-on-one questions. Please feel free to come up and ask. And there is still some cognac in the back. Thank you all.